Let's talk about continuity. So what is a continuous function? So let's do first the picture. So we are going to state the definition of continuity for metric spaces, but we are going to visualize it as a real function because otherwise no chance, right? So let's say this is our f, and typically a function is continuous as long as we can draw a graph, right, without lifting the pen. That's the image we all have about it, but that doesn't have any meaning in general metric spaces. But anyway, so let's say we want continuity at the point P. Okay, and this point P, but we are going to have the corresponding image, f of P. And continuity means that if we have, instead of taking the point P, we take a point close to P, then the images of those points that are close to P are going to be close to f of P. Okay, so somehow it's sending this, let's use green, it's sending the interval of points that are close to P to the interval of points that are close to f of P. And it's clear from this picture I did in this particular case that if we shrink the interval here, what we are going to see is a shrinking of the interval in the image too. Okay, it will be a correspondingly small interval. Now, you may be wondering, well, okay, so that's when it works. But what happens when it doesn't? Let me copy paste this axis. Oops. There we go. Well, that didn't quite work, but anyhow. Let's say we have some function that is just a jump function. Okay, so it's a function that jumps, let's say from 1 to 2. Okay. And we have our point P, that is the point where there is a jump. So in this case, whenever we take some interval around P, that can be as small as we want, what is going to happen? So some points, actually let me continue with green, some points will, the points on the right of P are going to map to 2, okay? So those are going to land in here at 2. But then the points on the left of P, they're going to land here with a value of 1. And that's it, there is nothing in between. Okay, so in this case, actually we have that 1 is our f of P. Okay, and what happens? Whenever if we shrink this interval here, this point 2 is fixed away from 1. So this distance between the images, that is not going to get any smaller, okay? And we can shrink this interval as much as we want, but this distance here is not going to change. Okay, so you see the behavior is very different for the continuous function. The closer we are to the point P, the closer we are to f of P. Okay, in the discontinuous case, no. So now what we need to do is to write this down mathematically. And that is the definition of continuity. So again, we have XY metric spaces. E in X, P in E, and F mapping E into I. Okay. So then F is continuous at P if and only if, this is a definition, for every epsilon there exists some delta. Okay, so we have our epsilon here and we have our delta. Sorry, the other way around. We have epsilon for the y's and delta for the x's. Okay, so there exists a delta such that the distance, distance in y, of course, the distance between f of x and f of p is less than epsilon for all points x in E, such that the distance between x and p is less than delta. Okay, so here what we are saying is fix an interval as big as you want around f of p, and you can map it back. Okay, the way we did it when we were doing the heuristics was from x to y, but actually with the continuous functions we work it back. Okay, so we take the epsilon first, it's a neighborhood around f of p, and then we send it back to discover that actually there is some delta, okay, that gives us another interval where all the pre-images of the f of x are going to land. Okay, I'm talking, of course, with intervals and everything as if we are in R, but in the metric space, we don't say intervals, we just say neighborhoods. Okay, and that is what we are giving here. This is a neighborhood. Of course, if f is defined, well defined, and it's continuous, at every point of E, then we say that f is continuous in E, okay? So we need to check the previous definition at every point. And then I was saying about being defined. Of course, f needs to be defined at the point P in order to be continuous at P. Otherwise, it doesn't make sense. And finally, something that is very, very important about continuity, that we are going to write it as a theorem, is that this circles back to what we were saying before, okay? So here, if f is continuous, well, let's write f from E in x to y is continuous, let's say at the point P in E, okay? If and only if the limit as x tends to P of f of x equals f of P. Okay, so this is saying that if a function is continuous, let's look back at the picture. If x tends to P, then the image of f of x, of x, the image of x tends to the image of P. We see that on the picture. We could do it from farther away. So this would be our f of x, and it would converge to f of P. And one more property that is very important is that composition of continuous functions is continuous. Okay, so here let's say we have three spaces, x, y, and z, metric spaces, all of them, and we have two functions. Let's say we have f going from some e in x to y, and then we have some g that is going from y to z. Okay, and here, of course, we are going to want, let's write it like this. This is going to take e to some f of e. Okay, and that one needs to be in y, otherwise it's not going to work. Just imagine if this is your e and it sends it here, but then you have your y here, then there is no chance the composition is going to work. Okay, it needs to be the f of e, it needs to be contained in y, then it will work. Okay, like this, no problem. Anyway, so let's f from e in x to y, g from f of e in y, convert, mapping to z. Okay, let's keep it like this, just to keep it simple. Okay, and here what we are going to consider is the composition of both of them. So we are going to take g of f of x. So this is the composition of f and g. We will write f composed with g. Okay, sometimes we will say it's the composition or the composite of f and g. Okay, whenever we have this, if both of them are continuous, okay, the first one is continuous at some point p in e, and the second one is continuous at f of p, of course. Then 8 is continuous at p. Okay, so we are saying here that the property of being continuous actually transfers. For the proof, here we are going to have to apply the definition twice, okay? So we want to show that 8 is continuous at p in e. So the first thing we need to do is fix epsilon bigger than 0 given. Okay, but actually, because we are going to have to apply the definition twice, we will need to use two letters. What we do in those cases is use epsilon and eta. Okay, so I will get to that in a moment. So, but for now, let's fix epsilon. And then we need to use, the only thing we can use is the continuity of g and f. Okay, so because g is continuous at f of p, there exists some eta such that the distance between g of y and g of f of p, okay, distance in z is less than epsilon if the distance in y of y f p is less than eta. Okay, and this is for y different from, y in f of e. Okay, so here actually the eta is the equivalent of our delta. Okay, now this is the continuity for g, but now we also have that f is continuous at p. Okay, so that means there exists some delta bigger than 0 such that the distance in y between f of x and f of p is less than eta if the distance in x between x and p is less than delta and x is in e. Okay, so you see here where's the trick. So we have, first we are using eta as a delta for the definition of G continuous, but then we are using eta as epsilon for the definition of F continuous. Let me make this more clear with a picture. So here we have our eta of P, which is G of F of P. Okay, and this one is inside the neighborhood. And this neighborhood has some radius epsilon that is given. Okay, so we are given this epsilon. And the definition of continuity, okay, the continuity of F, actually G, sorry, is saying, because G is applied second, is saying that as long as any point, how do we call them? Y. As long as we have points y that are within a radius of eta from f of p, the images, wherever they land, okay, that will be g of y, they are going to be within a distance of epsilon from f of p, from g of f of p, okay? So in this particular case, this point here is going here. But now, if we take one step back, here we have our P, which is in a neighborhood with some radius delta. Okay, and if this delta is small enough, we can be sure that our F is going to map it to the neighborhood of radius eta of f of p. Okay, and here what we were saying, we will have some point x, okay, that is what is going to be mapped, okay, to a point f of x, okay, that is going to be within eta of f of p. Okay, so this is what is happening. But then we can actually just cut the middleman. Okay, and we have our definition with the epsilon and delta. And just to finish the proof, what we have shown is that the distance between hx and hp in z, okay, which is the distance of gfx minus gfp, sorry, not minus, comma, okay, this is less than epsilon if dx xp less than delta and x is in E. This is what we have shown, and that means that H is continuous at P, which is what we wanted, and the proof is done.